Now I want to talk a little bit about symmetry of harmonic analysis. Remember, circling back to the idea of unification. We want unification in mathematics. There are different areas of mathematics, different subjects in mathematics. We talked about number theory, we talked about geometry. Now I want to talk about harmonic analysis, another continent in the world of mathematics, which has to do with harmonics, with the sound waves. And the simplest sound waves are sine and cosine functions, right? We can draw them like this. What is special about the sine and cosine? It's again, there is some property with respect to a group of symmetries. A sine and a cosine is a periodic function. Each of them is a periodic function. If you shift the argument by 2 pi, which of course 2 pi is a euphemism for 360 degrees, right? If you shift by 2 pi, it stays the same. Likewise, it's the same for sine and cosine. But what does it mean? What if I shift by 4 pi? It will still be the same, because shifting by 4 pi is the same as shifting by 2 pi and shifting again by 2 pi. Each time it will not change, so 4 pi will not change either. 6 pi will not change. Negative 2 pi will not change. There's a whole group of symmetries of the line which acts by translation, by shifts, by multiples of 2 pi, by 2 pi, 4 pi, 6 pi, and so on. And this group is in these functions, these two functions are invariant under this group. Invariant means doesn't change under these transformations. That's what's so special about sine and cosine function. And actually more general functions, sine of multiple of x or cosine of multiple of x, where the multiple is an integer itself. So geometrically, you can think about it like this. There's a typo in this picture, though. It should be 0, 2 pi, 4 pi, negative 2 pi, negative 4 pi. But that's the idea, that there are shifts. There is this, the function is defined, sine or cosine, is defined on the entire real line. But we only need to know it on one of the intervals, because then we will know what it is on the other intervals by shifting, right? Because the function doesn't change under the shifts, and therefore, if we know it from 0 to 2 pi, say, we'll know it from 2 pi to 4 pi. That's how it works. But more generally, so we can sort of take this idea and run with it, and consider more general spaces, not necessarily a real line, and more general symmetries, not necessarily translations like this. And we can study the basic harmonics, which would be the functions invariant under such transformations. And a great example of this happens when the space is a unit disk. There's a unit disk on the plane. A unit disk on the plane. The group which acts also has a fancy name, but now we are used to these names. We already talked about SO3 and SU3 and so on, SO10. So this is SL2Z. Z stands for the integers and a special linear group. It can be realized by 2 by 2 matrices whose entries are integers, and the determinant is 1. It doesn't matter. This is a technical issue. There is a certain group. What I've drawn here is how it acts. These triangles, you see these triangles that we have here, kind of curved triangles, they are the analogs of those little intervals which were on the previous picture. You know, here. Here, what played the role of an interval here is now played by one of those triangles. So the functions, the harmonics in this world will be functions which are determined by their values, and there are infinitely many of them. They're kind of becoming smaller and smaller. It's really a beautiful picture. And so these harmonics are called modular forms. So this is a very important example from harmonic analysis. So modular forms are like a sine function or cosine functions. It's the same idea, except we're now in a more sophisticated space, namely a unit disk, rather than on a line. And so now we come to the crux of the matter, the Langlands program. Langlands' idea was that the two continents of mathematics, number theory, which we talked about earlier, things related to solving polynomial equations and Galois groups, and harmonic analysis, the other continent, things related to, you know, decomposing the sound of a symphony into harmonics, or more general functions into harmonics on more general spaces. That these two worlds, these two continents are actually connected. There are hidden connections between them, hidden and unexpected connections. So it is like finding order in a seeming chaos. You get a problem in number theory, which typical problem in number theory would involve counting numbers of solutions of some equations. You can solve them on a computer in some small cases, and you generate a sequence of numbers. And they seem to be completely random and chaotic. But Langlands was able to reformulate that question in the language of harmonic analysis. And in the language of harmonic analysis, we could actually, one harmonic function, one modular form, one harmonic, can have the answer to all of those in one stroke. So it's almost like, I like to think of it as sort of like a source code. You're finding a source code of some intractable mathematical problems. So what's an example of this? Well, there's one example which pertains specifically to modular forms, which we just talked about. Remember that disk with those little curved triangles on it? And in this particular case, this Langlands statement, this Langlands correspondence between these two continents has been proved. And in fact, this is what led to the proof of Fermat's last theorem. Fermat's last theorem, of course, one of the most famous problems in all of mathematics. Pierre Fermat, a great French mathematician, realized that if you take equation x to the n plus y to the n equals z to the n has no solutions x, y, z in whole numbers if n is greater than 2. And he wrote about it on the margin of a book he was reading. It was actually Diophantus' arithmetic. And he said, I found a marvelous proof of the statement, but this margin is too small to contain it. Which I kind of like to think as a 17th century Twitter-like proof, It's like, I have this beautiful idea, but 140 characters, it's not enough to express. So the search was on for a proof, and for 350 years almost, actually more than 350 years, we did not have a proof until Andrew Wiles and Richard Taylor gave one. But it was based on a realization earlier by my colleague at UC Berkeley, Ken Ribet, in 1986, that actually Fermat's last theorem followed from that special case of the Langlands program that involves modular forms. So this is a big deal. It led to the solution of one of the biggest problems of all of mathematics, the Fermat's last theorem. But, it's only the tip of the iceberg. There are many, many statements like this which are still unproved, for which we still don't know the proof. And we still don't understand why. Even in the case which was used to prove Fermat's last theorem, which involves modular forms and Galois groups, which was proved by Andrew Wiles and Richard Taylor. Even in this case, I would say we still don't understand why. We can convince ourselves the math works out, but I still think that the jury is still out as to why this should be true, why these connections exist. They point to something really mysterious, kind of still beneath the surface. And that's why so many mathematicians find these ideas so fascinating. What's also interesting is that initially Langlands was really concerned about connecting number theory and harmonic analysis and obtaining some deep insights about both fields using these connections. But in fact, these ideas have since, we're talking about since late 60s, that's when Langlands first came up with these ideas. These ideas have propagated now to other areas of math and physics, to geometry in particular, and even to quantum physics. And this is something which, some recent work, which I have been involved with some wonderful physicists like Ed Witten at the Institute for Advanced Study in Princeton. And I won't tell you all the details about that, but I just want to mention that the connection to physics goes through what's called electromagnetic duality, which is a fascinating concept, which actually is something that we can observe by studying electric and magnetic fields using Maxwell's equations. So James Clerk Maxwell wrote this very beautiful, very elegant system of equations governing electric and magnetic fields in the second half of the 19th century. And electric field, we come to get to know electric field and magnetic field in very different ways, right? I mean, electric field is something responsible for the lightning, for example, and magnetic field is something that gives our, the compass, orients the compass in the right way. But it turns out that if you look at the equations and you exchange electric and magnetic fields in the equations, in Maxwell's equations, the equations will stay the same. Well, in vacuum, strictly speaking, in vacuum, but it's a very surprising property of the equations themselves. And so it's something you cannot really see if you just kind of go out and study, nature. And you would be seeing electric, you would be seeing magnetic, but it would be very difficult to see that the two are connected. It's only when you write the mathematical equations governing these forces that you can come to this realization. And this is somehow a very important element, I think, which is lost even on some scientists sometimes, which is, I think there is this sort of prevailing sort of impression of mathematics playing sort of a secondary role in science, that scientists get some data and mathematicians are trying to feed that data into some mathematical models. But that's not always the case. Sometimes, that, of course, is one of the important modes of operation. But we talked earlier about how Riemann discovered his Riemannian geometry without having any specific applications in mind, and yet it was very useful for Einstein's relativity theory, or about Gell-Mann talking, using SU3 for understanding elementary particles. And this is another example. We see electromagnetic duality by looking at the equations. So you have to first write down the equations which govern electric and magnetic forces to be able to come up with this insight. And so there's a beautiful story, continuation of the story, when we go from the sort of classical world of classical physics, low energies, large distances, to the world of quantum physics, high energy, small distances. And it turns out that physicists have theorized that something like electromagnetic duality might also be happening at the quantum level. And it is this quantum electromagnetic duality and its generalization in supersymmetry. So all the things that Robert Dijkgraaf talked about in the previous talk about supersymmetric generalizations of quantum theories, gauge theories, and so on. So when you look at this sophisticated quantum field theories, physicists theorized that they exhibit a sort of electromagnetic duality. And it was discovered in the last 10 years that that electromagnetic duality is intimately connected to the Langlands correspondence, to the kind of links and unexpected connections that we came to know through the work of Langlands. So there is a book that I wrote recently, it's called Love and Math, in which I talk about the Langlands program, and I give much more detail. You can find much more details about this, in particular, about this connection to electromagnetic duality. But if there's only one image I want you to stay in your mind after this talk, is this. A giant jigsaw puzzle. We're trying to solve this jigsaw puzzle, and there are different continents that we're trying to connect. And then connecting it to physical reality, to the physical world. Because, as Charles Darwin very aptly said, he did not like mathematics when he was a student. Surprise, surprise. It's true for most of us, I guess. It was certainly true for me. But then later in life, he came to realize that mathematics was important, and he said, I deeply regretted that I did not proceed far enough, at least to understand something of the great leading principles of mathematics. For men, thus endowed, seem to have an extra sense. And I'm not trying to imply that, gee, we mathematicians, we have this extra sense, so that's somehow very important. Because the point is that all of us have this extra sense, just like we have other senses. It's just for some of us, it's less developed than for others, but there is nothing to stop us from developing that sense and from connecting to these wonders of the world, which come from the world of mathematics. And it's really, I think, important point here also is that most of the things are still unsolved. We have, made tremendous progress, and we know many things. But the more we know, the more we know how little we know, right? And so each time, each solution, each problem, when it's solved, allows us to push the veil over the unknown, and we realize some problems which you didn't even know exist. And it's almost like Newton said, it's almost like we are like children playing on the seashore and diverting ourselves now and then, finding smoother pebble or prettier shell, whilst the great ocean of truth lay all undiscovered before us. So I say, let's go out and find more of those truths. Thank you very much.